And just to let everyone know what the structure of this exam review will be like, we will be spending about an hour and a half on just reviewing the material. Grace and I will be giving a brief presentation on some of the material you'll be seeing on your exam. After that, we have a couple of peer leaders from the SSC here to help moderate breakout rooms. So y'all will be looking at a problem set that you will be working on together with one of those leaders, so in a breakout room, so that y'all can get a little bit of practice based on what we say in the review. So, and I'll be getting started in a minute. Okay, I think we've had most people come in at this point. I'll get started. My name is Ria. I'm one of the peer tutors at the SSC. I'll be presenting the first part of the session. My lovely partner Grace will be doing the second half. If y'all are flipping through the PowerPoints, please don't do that. It makes it really hard for us to present, and if we do have to go back and share that PowerPoint on our screens, it's going to be more difficult for us. Yeah, and do let me know if something's wrong with my mic. I do believe it should be working right now, but I have been having some connectivity errors, so we will be seeing. But yeah, please make sure to not flip through the PowerPoint. Otherwise, we will have to take a couple more minutes to just reset that up in a way that you cannot. Okay, let's get started. So this first exam, actually, the second exam, it has quite a few different reactions on it, but we're going to try to see if we can summarize some of them in such a way that it's a little easier for y'all to find those rules specifically. So we're going to start with the halogenation reactions. These reactions you may have learned at the beginning of the unit, but these are also great reactions to help set up SN1, SN2, E1, E2 reactions because you'll be adding a halogen to an alkane molecule, right? So a free radical halogenation is exactly what it says on the tin. We're going to be adding a halogen to an alkane. So these halogenation reactions come in 3 steps. They have an initiation step, a propagation step, and a termination step. I think a couple of words got shifted around, but we should be able to read that. And essentially what we will see happen is we're going to first see an initiation step where we create radicals. I believe I have the wrong picture up there. Let me draw that up really quickly. We're going to see that we'll have an originally molecule that will break up to form 2 radicals, such with something like heat or light. Often use HV for that, and we'll see 2 radicals be created so that we can start the step. Now that we have radicals, we can use them to propagate and form a more stable product with one of them, and when they react with another molecule, and then also form a new radical. So situations like this, one example is that if we have a chlorine radical, it can come in and attack a methyl group such that it forms a bond with our halogen, and not our halogen, our hydrogen, and we will see this hydrogen leave and take one of those, its own electron away, leaving us with a radical on our alkane. And what happens at that point is we keep on seeing propagation. That same molecule can come in and also go and attack more chlorine molecules and create more radicals. This process does not end until termination, which is where we will remove those radicals through a reaction in between 2 radicals, 2 molecules with radicals on them. Each of those molecules will donate 1 electron, that radical, and they can form a bond such that we have finally got a stable product. We're not going to be seeing any more propagation at this point, right? And mostly You can also think of this in one step where we see Cl2 added to some alkane and forming chlorine on that alkane. However, it is important to be able to write out each of these steps and label them on your exam, as that will be important there. Right. Let's see if we can. Yes. And a lot of this comes in two flavors. We see chlorination and bromination reactions. There are other halogenation reactions, but these are the two that you will most likely see on your exam. In chlorination reactions, you'll see that they tend to be less selective. There are multiple products. And the reason for this being that chlorination reactions are exothermic. Our transition state is closer in energy level to our reactants than to our products. And because of that, we will see a lot more possible products. We'll see, and because of that, you will also be asked possibly to count the number of products found possible. And one way to do this is to use lines of symmetry so that you can make sure that you're not creating any repeat products when counting those possible products. And then we also have bromination reactions, which they tend to be more selective. You'll only be seeing a single product formed from these reactions because these are more endothermic. They're going to be requiring more energy to form. And because of that, we're going to find that our bromine is only added at the most stable radical position on a molecule rather than just any one like chlorination. Right. And that sort of leads into our next question, which is how do we determine the stability of a radical? And we have this lovely table here. And one thing to note is that radicals often, we're so focused on the fact that there's an electron on an atom that sometimes I've seen that students do forget that we are actually looking at something where we're looking at an electron deficient atom. So even though there is one electron on there, we are missing another, right? So we're going to see that radicals tend to follow the same reactivity trends as carbocations, which are when you have a positive charge on a carbon versus actually carboanions. So you're going to be seeing that radicals tend to want to be in a state where their electron deficiency is made up for by putting them on a tertiary carbon versus on a secondary primary, simply because that being on a tertiary carbon means that there will be more electron density surrounding your radical. You're going to be seeing a lot more sources that can sort of help even out that electron deficiency at the atom versus if you were to put it on like a methyl, there's nothing that can help make up for that difference. And some other things to note, resonance stabilizes all charges on atoms. So we're going to see it stabilizes our radical, our carbocation, carboanion. The reason being because it helps delocalize that charge often and just make everything a little less electron deficient or electron rich. And the final thing that we have to consider is inductive effect. We're going to be seeing with radicals and carbocations both, we're going to be seeing that electron donating groups are more stabilizing versus electron withdrawing groups, which take away electrons, are destabilizing. Simply because, again, we're trying to make up for the electron deficiency. We want to go closer to normal. So we want, if we're electron deficiency, we want more electrons to come our way. If we have too many electrons, like in a carboanion, we want electrons to go away from us, in which case electron withdrawing groups are stabilizing. I do apologize, this PowerPoint does say that they're destabilizing. I meant to say that this is stabilizing. Electron withdrawing groups stabilize carboanions, not that they destabilize. They would be destabilizing these electron deficient intermediates instead. And I think it got cut off in this PowerPoint, but some things to note as well are what does it mean to be electron donating versus electron withdrawing? Some examples that you're going to see are that electron donating groups tend to be methyls. You're going to see methyls. ethers, and I believe amines. These are some good groups to look out for. Also hydroxyl groups, which are just OHs. And then some electron withdrawing groups that you're going to be seeing most commonly are going to be carbonyls and halogens. Right. So when you see any of these groups, you can consider, it's always important to consider when they're surrounding a radical or a positive or negative charge is this electron donating or withdrawing, and is that exacerbating my condition? Is it making it more electron deficient or less? And essentially that is the essence of determining reactivity of any of these intermediates. Moving on, we're going to be looking at what is really the meat of all of organic chemistry going forward, which is nucleophilic substitution reactions. We're going to be looking at SN1 and SN2 reactions. And at its most basic level, what a nucleophilic substitution is, regardless of SN1 or SN2, is that we're going to be seeing some nucleophile react with an electrophilic organic molecule. Often this is an alkyl halide, which is just your classic garden variety, just halogen attached to your alkane, right? And nucleophiles, some basic definitions for this are that nucleophiles tend to be attracted to positive charges. They tend to have a lot of electrons. They're electron rich. They're trying to give away those electrons. Our electrophiles, on the other hand, are typically more electron deficient. They are attracted to that negative charge. They want those electrons. So, you know, a match made in heaven. They both need what the other has. So it's perfect. And this is where I am going to list these as 2 steps, but it's important to consider that this can be combined or separate depending on the type of reaction we look at. What you're going to see in both of these SN1 and SN2 reactions is that leaving groups, we're going to see a leaving group such as like our halogen in this alkyl halide. We're going to see that leaving group leave, and in its place, we'll see a nucleophile form. However, this is listed as 2 reactions, but it can be either like together or separate. And that really is what distinguishes our SN1 versus SN2 reactions. Right. So we're going to be looking at SN2 reactions first. Oh my. Please don't flip through the slides. It is going to break up our session more, and it's going to make it harder for us to get this information to you. So you don't need to touch any of those arrows. I'll be going throughout the entire presentation. But we're going to be looking at SN2 reactions in which we will see that that step that we were talking about before, where we first see the leaving group leave and that nucleophile come in and take its place, it's going to be a 1-step reaction. It's going to be concerted, which just means like it's 1 step. Our nucleophile comes in, it attacks, and it pops off our leaving group. And after that, we see our leaving group leave, and our nucleophile takes its place, all in 1 step, right? We're not going to be waiting for anything to happen. This is a really fast reaction. Some things to note are that in order to have an SN2 reaction, you must have a strong nucleophile and a substrate that is willing to react. It has to be not sterically hindered, and it has to be somewhat unstable. In addition to this, we'll also see there's going to be an inversion of stereochemistry when this reaction happens. You're going to be seeing when our nucleophile comes in to attack, whatever, if our leaving group was on a dash, we're going to see the nucleophile form on a wedge. If it was on a wedge, it'll form on a dash. And that's simply because there's not a lot of space. This reaction is happening really quickly. We're just going to flip the stereochemistry really quickly. And that is something that you will be tested on. Make sure that if there is any kind of stereochemistry on your exam, that you are changing it, because that is very important for SN2 reactions. We also have SN1 reactions, which are a slower kind of nucleophilic substitution, and they are considered two-part reactions. They first have the same order. We are going to see a leaving group leave first. And in that case, carbocations will be formed. A carbocation will be formed. At that point, after that carbocation has been formed, we'll say, okay, now the nucleophile can attack because it is more willing to do so. Something important to remember is that our rate determining step is carbocation formation. We're going to be seeing that the carbocation will be formed, and that really is going to take the most time. We're going to be considering that because of that, when we look at an SN1 reaction, we really only consider substrate properties. It doesn't matter if the nucleophile is strong or weak. It really just matters, is our substrate in a position where it can stabilize a carbocation better or worse, right? And something else to consider is also rearrangements. Rearrangements are possible because when we're creating that positive charge, we'll see it rearrange before our nucleophile attacks. We're going to see majority products and minority products. You're going to typically find the most stable position for that carbocation and just place your nucleophile there, right? And to get started, one of the most important distinguishing factors between SN1 and SN2 reactions is nucleophilic strength, right? So in this case, it's specifically that SN2 reactions require strong nucleophiles. SN1 does not care, but you must be strong in order to get through an SN2 reaction, right? Some factors to consider are that we're going to be seeing that having a charged molecule tends to be more preferred. You're going to see specifically a negatively charged molecule is typically more strong as a nucleophile than something that is not charged, and that's simply because we have actively got more electrons. We're seeing maybe even a destabilizing effect because of that, which makes it more reactive. In addition to this, we're also going to see that we're going to see trends that follow our mnemonic bean, which is on our periodic table. If we label it such that we have B, E, A, and N, our nucleophilic atoms will tend to be, you're going to see that we're going to be trying to go down the periodic table and to the left. And the reason being, you want to have a less electronegative nucleophile or less electronegative atom, simply because you want to be more willing to donate those electrons in a reaction. You're ready to pop those off, give them to that electrophile, right? So you don't want to be clinging on to them. And similarly, we also are looking for a larger atomic radius because that causes the molecule to be more polarizable, and also it allows for more overlap between molecules so that we can start creating bonds. And finally, something to consider is that we don't want to have a very bulky nucleophile. We're going to have something that minimizes steric hindrance. It's going to be small. It's going to be able to get into those spaces such that it can come in and do a backside attack. Like when you're trying to be sneaky, you're not going to send like the hulking soldier. You're going to send someone who's like tiny to go and investigate and go and attack, sort of sneak attack, right? So here, in the same way, when we have a backside attack, we want to have a small nucleophile. We want to have something that can get through and quickly create these reactions. It shouldn't be lumbering around trying to get in. And so because of that, you're also going to see that you're going to want your main atom, to be on the primary. You're going to want it to be on a primary versus a secondary, tertiary. Right. And next, we also have to consider substrate reactivity. This is important for both SN1 and SN2 reactions, but we see opposing we see opposing trends. Specifically, we're going to be looking at the position on which carbon our leaving group is placed in an SN2 reaction. We can continue with that one first. we're going to see that we prefer to have less steric hindrance again. We're going to want something where it's easy to come in and attack. So we're going to be saying, yeah, we will be having this PowerPoint sent out to all of y'all, and it will be on our YouTube page as well. But our SN2 reaction will see that we prefer less steric hindrance. We're going to be preferring primary carbons to secondary and tertiary. And something to note is also that our one major fail factor is it's impossible to have an SN2 reaction occur if a leaving group is adjacent to a quaternary carbon. That means, like, say I have my chlorine and I have like the strongest nucleophile ever, right? Strong nucleophile. It doesn't matter if this carbon over here has got 4 bonds, if it's a quaternary carbon, right? Cannot be an SN2 at that point. Similarly, our tertiary will also be very slow to happen. You will typically prefer to go SN1 if you see your leaving group on a tertiary carbon. In addition to that, we also have to consider leaving group stability. So we have to consider its position, but also what exactly is it. More stable and unreactive, sorry, just had a brain fart, but you're going to be seeing that our leaving group should be ready to leave, and it should be stable and unreactive after it leaves. Specifically, it's not dying to go back. It's left. It's not coming back. It's got its own life now. Goodbye, old electrophile. Hello, new life, right? So we're going to see that we typically prefer to have large electronegative atoms, because when they leave, they may leave as anions. They're going to take away those electrons. And because of that, they need to be able to stabilize that negative charge. So oftentimes you will see the most stereotypical leaving group is our halogens. And that is because our halogens are very happy to leave with a negative charge, right? They want that electron and then they're out, right? Or those electrons and then they're out. So they are going to be fine having a negative charge. They're not going to be super reactive after that. So a lot of good leaving groups tend to be something like halogens. We're also going to see that if they're charged, are halogens. We're also going to see that if they have a positive charge on them, they tend to also be good because they will be leaving with those electrons, thus neutralizing that positive charge. And yeah, something to consider as well is that if you do end up with a very neutral leaving group that includes alcohols, amines, and ethers, you're going to want to protonate them by adding a hydrogen such that they are more destabilized, they're more willing to leave and just stay gone, right? As such as even this one, this is just water we will be seeing, which can leave really easily, right? And then in the same way, we're also going to be looking at SN1. I think I skipped that before. SN1, it has opposite trends in terms of reactivity based on the position of where the leaving group is. Leaving group stability matters for both SN1 and SN2, but SN1 specifically also wants to see that our leaving group is in a position where we can stabilize a carbocation. So we want to have more crowding. We want to have like sort of a large number of groups coming around who can help keep that positive charge happy, more stable, right? So we're going to see that in general, we're going to prefer tertiary, the form like a leaving group on a tertiary carbon or a secondary carbon over a primary. And that's simply to stabilize that carbocation, right? And then something to consider as well is in SN2, we talked about how we're going to see a concerted reaction. We're going to see a one-step. But SN1 is a bit different, right? In an SN1 reaction, we're going to be considering our carbocation stability. But when we do, we don't necessarily always have to consider it based on what leaving group, where the leaving group is positioned. It's really on where the carbocation is positioned. So in this case, some things that we can do to create a more stable carbocation and create a more effective SN1 reaction is we have a couple of rearrangements that can occur. The first one being that we can have a hydride shift reaction. This is the most common one that you're going to see. You're going to see a hydrogen move over such that we can have our positive charge in a better position. It's just going to move to, it has to be adjacent to our positive charge, but once it moves, say like we're going from here in this picture, we're going from a primary location to a tertiary, right? That's really great for our reaction because now I am in a more stable position to have an SN1 reaction occur, right? So like going from a primary to a tertiary is, and some very important to remember, you can't move it like 3 spaces over. It has to be to the adjacent carbon, sadly enough. We're also going to consider a methyl shift in which we can see the same reaction happen, or not the same reaction, but the same sort of rearrangement happen where our methyl can come up if there's no hydrogen available and shift to the position of that positive charge, letting the positive charge come down as now there's no bond here to provide those electrons. And one thing to note is if it's possible for there to be a hydride shift, we're going to prefer that to a methyl. So don't go too gung-ho about that. If there's a hydrogen, first check if there's a hydrogen adjacent that can put our carbocation in a stable position. If not, then we can do a methyl shift. Otherwise, we do prefer to have a hydride shift happen first. In addition to that, we also see our final one is a ring expansion. And what this means is if we see that our positive charge is adjacent to either a four-membered, or okay, a 4 or a 3-membered ring, we're going to see that here. No, not 4 or 3, 4 or 5-membered ring, 4 or 5-membered ring. We're going to see that we're going to try and expand that ring because it's currently in a less stable position. Our ideal is to have a 6-membered ring. So in a case like this, we would see that our ring expands such that this bond breaks over here. Let me grab my pointer. This bond over here breaks so that we can, and those electrons come in and they attack at this other adjacent carbon such that we can form a more higher membered ring structure, right? So a 5-membered ring is more stable than a 4-membered ring, but also if you see a 5-membered ring in the same position where we have the same idea going, we're going to see the same breakage occur because up until we can form a 6-membered ring. So just something to consider. I know this one tends to be a little more intimidating for our students. It's something you have to consider, though, that if our carbocation is adjacent to a 4 or 5-membered ring, we have to expand it. If that would be more, because that would make it much more stable. Oh, yes, and the positive charge does move over here, yes. Right. And so just in brief summary, and yeah, if it's not, if the ring has more than 5 members, so 6 members, it's going to stay in that position. You'll see that cyclohexanes are like the prized child of organic chemistry. We really like to see them. Benzene is a fun one, right? But we're going to be seeing 6-membered rings are preferred. After that point onwards, we don't do ring expansions. Right. But a brief summary of SN1 versus SN2 reactions, really some things to consider are, first of all, that SN1 reactions are, they only depend on the substrate. So we're also going to see that that means that our rate will be solely dependent on your substrate. You're not going to be considering our nucleophile at all. And it's considered a unimolecular reaction because of that. In addition, but on the other hand, SN2 reactions, you're going to see it's bimolecular because we have a concerted step where our nucleophile comes in and causes and interacts with our substrate to create that formation. It is a single step. We're going to see that both our substrate and nucleophile are involved in moderating the rate of the reaction. Some other things to consider is that nucleophile strength only is important for SN2 reactions. If a nucleophile is strong and it meets all of the cases, you're going to go SN2. If it's strong and it violates, say, like our substrate has the leaving group on a tertiary carbon, or if it's adjacent to a quaternary carbon, then we will go to SN1. So SN1 reactions can have strong or weak nucleophiles, but only if it fails, like a strong nucleophile, only if it fails to have an SN2. Some other things to consider are also that our substrate preference trends are opposite. For SN1 reactions, we're going to be trying to stabilize our carbocation. And because of that, we're going to see that we're going to be looking to have more substituents nearby. We're going to look for tertiary and secondary over primary and methyl groups. On the other hand, SN2 reactions, it's really important to have a non-sterically hindered substrate, something that has not got a lot of electron donating groups around either. We're going to be seeing a preference for primary or secondary a carbon position over tertiary carbons. If a leaving group's on a tertiary carbon, it's very unlikely that you're going to have an SN2, and it is impossible if you have your leaving group adjacent to a quaternary carbon. In addition to this, some basic things that I did not entirely touch on are solvent. This isn't too important when choosing between an SN1 and SN2 reaction, but solvent can moderate how quickly a reaction happens. In an SN1 reaction, you're going to prefer to have a polar protic solution, a solvent, because that will help stabilize our positive charge again, right? Versus an SN2, we're going to want something that's polar aprotic because we don't want to have additional reactive like positivity that can help distract that nucleophile, right? So something to consider is that SN2s, they require polar aprotic, SN1 polar protic. You may be asked a question where you will have to distinguish between the rates of two SN2 reactions. You have to consider you may have to consider the solvent in that case. Some final things to remember for SN1 and SN2 reactions are also for SN1, you're going to be looking for rearrangements. Make sure that there is that you have the most stable position for that carbocation. Check for rearrangements, check for even if you can use resonance to move it, just have the most stable position. SN2, it's a one-step reaction. The one thing that you have to remember is just that we have to invert that stereochemistry. If it's on a dash, it goes to wedge, wedge to dash, right? But that really is the essence of our SN1, SN2 reactions. We're going to be moving on to look at elimination reactions, which is Grace. So I'll hand it off to her.
Thank you, Ria. So just like she said, we're going to move on to elimination reactions, which is kind of the second half of these set of mechanisms that we've learned in this unit. So with elimination reactions, we kind of have two things going on here. We have E1 and E2. Both of them have a leaving group and a hydrogen both leaving the molecule, which is different than the substitution reactions where you would just remove the leaving group and add on another molecule. But this one, we don't add any new atoms. We're creating a double bond. And so this double bond can actually be formed in one of two patterns. We have the Zaitsev product and the Hofmann product. And so the Zaitsev product is going to be what you see most often. It's the most stable, and it basically just refers to where the double bond would form, with it having the greatest number of substituents on either side of the double bond. And since we know that more substituted alkenes are more stable, that's why Zaitsev is more common. But there are a couple cases where we might actually make a different product called the Hofmann product. And that's actually just basically where it goes to wherever the Zaitsev product is not. So it'll form where there are less substituents on the alkene at the end. And so this happens when you use a bulky base in E2, or if you don't have an anticoplanar hydrogen on E2, which we'll talk about later, of course, But basically, there are just a couple instances where you might make the Hoffman product, but once again, it is less common because the final product is not as stable as the side-F product. And then finally, eliminations are a result of strong basicity. So typically this will happen if you have a weak nucleophile, or for some other reason you can't do a substitution, so you'd want to do an elimination with a base. So E2 we're going to go over first because I think you guys learned it first, but it's also just a lot of special things to cover. So basically, E2 is a one-step reaction. It's going to want to occur more often than E1 because since it's concerted, it'll happen faster. It can all happen in one step and be done. So if a reaction can do E2, it will. So basically, what happens is a strong base removes a proton and a leaving group leaves, forming a double bond. And so I'm just going to be flipping back and forth between this and the next slide, so don't be confused. I'll come back to this. But here's the mechanism of this. So like I said, there's this base that's attacking the hydrogen that's one carbon away, called the beta carbon, from the alpha carbon that has your leaving group on it. And so once it attacks that hydrogen, the hydrogen's electrons from the bond go in between the carbons to make a double bond. Whoever is moving the slides, please don't. It moves them for everyone, so it's going to mess up the presentation. But anyway, so then because we now have the double bond in between the carbons, that other carbon, the alpha carbon, can't have that many bonds, so it has to make something leave, and that's why we see the loss of our leaving group. So then back to this slide. E2 is a bimolecular reaction, hence the 2 in E2, because the base and the substrate are both in the rate equation. And so that's why we need a strong base, because base is in the rate law. You'll see that this is different for E1, and we don't really care about having a strong base. It can be weak because the base is not in the rate law, so it really doesn't matter the strength. So similar to E1 and SN1, it prefers tertiary over secondary over primary. And then this also prefers polar aprotic solvents, similar to SN2. So it's kind of taking characteristics of every other type of reaction. So some examples of polar aprotic solvents would be DMSO, acetone, DMF, and DME. And then, like I mentioned earlier, this requires a strong base because the base is in the rate law. And so an example of some strong bases would be OH, O, and any other kind of alkyl group, an amine, a methyl, and a hydrogen even. And then there also was this chart, I think, on this. Yeah, here's a really good chart. If you just look up on Google strong and weak base and nucleophile chart, this is the first chart that shows up, and I highly, highly recommend memorizing the columns on this chart. It gives like most of what you'll see. There might be a few exceptions, but you probably would have covered those in class. But if you can remember what's on each of these columns in this chart, that will really help you with knowing which mechanism you're going to follow. Because like we've been talking about just now with E2, you need a strong base. So you can't have like an alcohol being your strong base because that's weak according to this chart. So that would help you know that we can't do E2 with those conditions. But anyway, that's just a little side note. So back to this slide again. With E2, the most important thing I would say about this that distinguishes it from E1 is that E2 is stereospecific, meaning that there must be a hydrogen anticoplanar to the leaving group or the reaction will not occur. So anticoplanar means it's on the adjacent carbon with the opposite stereochemistry. So if your leaving group, let's say, is a bromine on a wedge, then you need to have a hydrogen on a dash on one of the carbons adjacent to the carbon that the bromine is on in order for E2 to happen. Otherwise, if there's not one, it'll either switch mechanisms altogether or it can make the Hoffman product, in which it will just go to the opposite carbon if it can find an anticoplanar hydrogen over there. So basically, this will still prefer side-F product because it's more stable. But if we're using a bulky base, and also just based on that chart, The two bulky bases you'd want to know are in the weak nucleophile strong base category. It's LDA and then potassium butoxide. Those are the two that I definitely know. So it's not labeled on this chart, bulky base, but just know those are the only two things in that column. They are not good nucleophiles, but they are strong bases, and you have to recognize that they're big and bulky. So if you use those, it doesn't matter whether there's an anticoplanar hydrogen, because it's so bulky, you want to go to wherever there are less substituents. So that's the one case where it's always going to make a Hoffman product if you use those certain reagents. Because, I mean, the whole point, like I kind of just mentioned, is like these are really big. And so there's going to be a lot of steric hindrance if it tries to make the product on the side that has more substituents. And so what it's going to do is always go to the other side, which corresponds to the Hoffman product. And so at the end, the alkene will be less substituted. And then finally, E2, you cannot do any rearrangements similar to SN2 because it's a one-step concerted mechanism. Oh, sorry, I just realized people were asking questions over there in the chat. Can you use E2 if your carbon is connected to a neopentyl instead of SN1? Oh, it looks like Justin answered this. Yeah, so anyway, because this is a one-step mechanism, there's no chance for us to rearrange because rearrangements happen to stabilize a carbocation intermediate, but E2 does not have a carbocation intermediate because, once again, it's only one step. So let's just take a look again at this mechanism. We see the double bond forming in between the alpha and beta carbons that have, it doesn't have stereochemistry listed specifically here, but because they're only di-substituted, we can assume that we have H's in both positions, so we know that we have one that is. Okay, can you explain more about Hoffman product? Yeah, sure. So Hoffman product is when you would be forming the double bond in the direction that will lead to a less substituted alkene at the end. Okay, so whoever is moving the slides, please don't do that. Okay, we're going back here. So let me go ahead and draw, like, on this one, the Hoffman product would not occur because we do have an anticoplanar hydrogen, so that wouldn't be an issue, but it would kind of look like that if we did, as opposed to the one that's written. Because the one that's written, you can see at the end, we have a trans di-substituted alkene. And so that's going to be the most substituted alkene that we can make. But the one that I drew right above it in blue is what would happen if we took off the hydrogen from like another direction or something like that. So basically, like at the end, we have just a monosubstituted alkene, which is less stable. And so that's what's going to be considered the Hoffman product, which is going to be made, once again, if we use either a bulky base or if we can't find an anticoplanar hydrogen on the side that would make the Zaitsev product. Does that make more sense, I'm hoping? I'm not sure who's still moving the slides. They will be posted afterwards, and once again, it changes the slides for everyone in the room if you click those arrows. So hopefully that cleared up about Hoffman product. Awesome. Okay. So now moving on to E1. So E1 in a lot of ways is simpler because you don't really have to worry about the stereochemistry and stuff like that. So similar to SN1, E1 is two steps. The first step is the leaving group leaves, creating a carbocation intermediate. And then the second step is that the proton leaves, which can then form a double bond. So this is a unimolecular reaction, which is what the 1 comes from in E1, because our rate law just has the concentration of the substrate in it, which of course you're not going to have to plug anything in. This isn't Gen Chem, don't worry about that. But that's just to show that the base strength is not important because we don't see the base concentration in the rate law at all like we did in the E2. So that's, you know, just kind of the reasoning behind why don't we care about whether the base is strong. Well, it doesn't affect the rate, so it really doesn't matter. This has the same trend as E2 in terms of the substitution level of their substrate. The tertiary is going to be preferred over secondary, which is preferred over primary. And this, the reason that it's good for E1 is because this will stabilize your carbocation intermediate. So that's why it also takes the same trend as SN1, because that's the same reason why I want it to be the most substituted as possible there, because a carbocation is an electron deficient, well, it'll make whatever that atom it's on electron deficient. So then if we have some more electron donating groups in the forms of like methyls, just basically any kind of alkyl chain, that will help offset the electron deficiency, which is why we want it to be more substituted. So this one prefers polar protic solvents like SN1 does, and examples of these would be water and alcohols. Like I mentioned, there's no stereospecificity on this one, and that's because we can rearrange. So we have our carbocation intermediate, and we have time to kind of move around if we need to. So it still is the same way in that you would need an anticoplanar hydrogen, but since we have an intermediate step, what you can do is rotate around to get your hydrogen in the anticoplanar position. So for that reason, you can almost always achieve the side-step product in E1. I don't think there's ever a case where you would ever get a Hofmann product, because you're using a weak base here, and you can rearrange your carbon with the hydrogen on it to be however you want to make it anticoplanar. So for this reason as well, rearrangements are possible and they're likely. So Ria mentioned earlier in the PowerPoint the different types of rearrangements that we had in SN1. The same thing is true for E1. We can have hydride shifts and methyl shifts. I don't think you see ring expansion necessarily as often with eliminations, but it probably can still happen. And then you watch out for dehydration of alcohols. So that would be where a proton would combine with a hydroxide to leave as water. And then another thing to note about E1 is that it competes with SN1. So I would say E1 is different than all of the other mechanisms, because all of the other mechanisms have some kind of condition where it's going to be preferred. And E1 doesn't really have that. You know, it doesn't really have a certain set where it's like, oh, if you have this and this, E1 will happen. Even if E1 does happen, it's still competing with SN1. So all of that is to say that E1 doesn't happen very often, because you'd want to have a weak base. E2 doesn't always compete with SN2, because E2, remember, needs a strong base, and SN2 needs a strong nucleophile. And so if you only have like one or the other, then it's going to do each one. And then the other important thing to remember is that they prefer different substitutions of their substituent, or of their, I just said the same thing. They prefer different substitutions of their substrates. So SN2 would prefer primary and E2 would prefer tertiary. So they would not compete with each other because they want completely different sets of conditions. But E1 and SN1 want the same conditions. So that's why these will compete, because they both want tertiary, and they both just have like a weak nucleophile, weak base kind of thing going on. So if E1 happens, there will also be a mixture of substitution products as well. So taking a look at our E1 mechanism, we see the two steps that I mentioned where you lose the leaving group and then the deprotonation step. What we're seeing here is our bromine is taking our electrons so that we have a carbocation where it used to be. And now, because our OH2 is a base in this situation, it is going to want to rearrange so that we can have a more substituted carbocation. But basically, since we're not adding anything on, you'll end up just seeing that we create a double bond in between the two where the hydrogen and the bromine used to be. So we don't see any stereochemistry here, also because we end up with an alkene, so there's going to be no stereochemistry involved in the product anyway. So this is a really good chart if you're ever confused about, I have no idea what mechanism to use, it's so confusing to me. This would be a good thing to memorize. So if we have, it'll show like if your substrate is primary, secondary, or tertiary, wherever your leaving group is on, and then it's paired with either a strong base, weak nucleophile, and then of course it goes weak, strong, strong. Then it'll show you the mixture of products that you can create. So, like I was mentioning, E1 hardly ever happens. It takes up like half of that box. And even in that box, it's competing with SN1 when you have a weak base and weak nucleophile on a tertiary leaving group. So SN2 is going to be most preferred if you have a lowly substituted substrate, and then if you have a strong nucleophile. Where if you have a strong base, but your substrate is more substituted, then it's going to go towards the elimination product through the E2 mechanism. SN1 is the primary product if you don't have a like lowly substituted substrate. So even if you do have a strong nucleophile, but you're on a tertiary, you don't want to do SN2 because that's going to be too hindered. So that would be a situation where even with a strong nucleophile, you might actually do SN1 because SN2 with the steric hindrance, it can't have too much going on. So once you get up to tertiary, we're going to switch over to SN1. But basically, all of these things can be reasoned through the things that Ria and I have mentioned throughout this PowerPoint, and it would be a good thing to know in terms of practicing which mechanisms that we're going to be using on any given situation. And then this is a chart courtesy of Justin, who's been in the chat helping you guys with your questions. It's another way to kind of determine what we're going to be using. So our first question is our nucleophile strong? And if it's yes, then you could be doing SN2 or E2, which there are cases where you might have a strong nucleophile weak base, so then it probably wouldn't do E2, but that's pretty rare. I think most strong nucleophiles are also strong bases. And so if you're doing SN2 or E2, remember SN2 is the only mechanism that prefers primary over tertiary. And that's once again because SN2 happens very quickly. It doesn't want a lot going on. So if you have a lot of extra substituents, that's going to take up a lot of room and it's going to just crowd the whole situation. So it wants primary. So then if it's tertiary, you're going to be going towards E2 because there's just going to be too much going on for SN2 to happen. And then if it's secondary, you kind of need to look into it more. That one can kind of go both ways. And then if there's bulky base, is E2 always preferred? Bulky base always equals E2. That's a good question. So if there's a bulky base, it's going to be E2 mechanism pretty much no matter what. So the stronger bases prefer elimination, as do substituted nucleophiles, meaning not primary. So if it's primary, it's going to be doing SN2. But if you keep getting more substituted, it will go more towards the elimination product. And then it will, as it increases in polarizability, that enhances the nucleophilicity and it will lessen basicity. So like Ria mentioned earlier with our beam trend, I think I might be able to draw it on here. So I've been having some difficulties with the drawing, but pretend this little box is a periodic table. And then we have our beam trend here. So with our bases, electrophiles, acids, and nucleophiles, that's what those letters stand for. So you'll notice the best nucleophiles are more polarizable, and then that will also make it a worse base because the bases would be at the top of the periodic table and the nucleophiles would be at the bottom. And then if you also have branching near your leaving group, or if the adjacent carbon is quaternary, that will prefer elimination. Quaternary in particular, like Ria mentioned earlier, will never have SN2, ever. If there's a quaternary next to where you're trying to do SN2, you cannot do SN2. So that's definitely something to make sure about because I can almost guarantee you're going to have some kind of ranking problem, ranking substrates for SN2, and there's going to be a quaternary next to where you're reacting. And maybe it'll be like a primary. So you're like, oh, that's going to be great for SN2. But you have to look around. You have to kind of see what's going on around it. And if there's quaternary, no SN2. So going over to the other side, where if we did not have a strong nucleophile and we want to do SN1 or E1, both of these prefer tertiary and they can react with secondary, but they will not likely react with primary. So one special thing to note about these is if you see silver nitrate, it will guarantee you one of these, and I would say it's almost always SN1 as well. I always associate silver nitrate with SN1. With these, you always have to check for rearrangements because they both have a carbocation intermediate. And then there will be competition between these two mechanisms, but the exam will typically specify which product it wants. I know some professors will say if you add heat, it's more likely to prefer the elimination product, but this is kind of back and forth because I don't know if all the professors agree on that, and then sometimes it's not written, there are exceptions. So I think for most of the time, when you have a situation where these two would be competing, which would be like a tertiary substrate that was weak nucleophile, weak base, it would probably specify to you or tell you to do both in terms of which product that it wants. So you won't be left stranded as long as you understand that those are competing and that you would need to provide both unless they asked for just one or the other. All right. So that concludes this portion of our review for today. So next we're going to have breakout rooms where you guys will be put into groups with one of the leaders here, and we have a whole packet of practice problems that we're going to work through together. And then once again, in case you missed it, everything will be provided to you, posted somewhere after the presentation. So this PowerPoint will be included, the practice problems will be included, the key to the practice problems will be included, and this recording, because we've been recording this, and we'll be recording a breakout room as well. It'll all be provided, so do not worry if you missed anything. So thank you for attending this portion, and just sit tight while we put you in a breakout room.
So let's start with some ranking. So first we have some rank by stability of each carbocation. So if we remember our carbocation stability, what we'd like to do is tertiary, secondary, and primary, and of course resonance is going to be greater than all of them. So based off these, let's label them like this. First, I'm going to look for any resonance stabilized carbocations. So this is one, and this is one. So let me see if I can make a poll. One, two, three. All right, so I made a poll right now just for about the three options. So out of these three, which one do y'all think is going to be the most stable? So we have one answer for three. Okay, we got a couple answers for three. And you are correct. So 3 is going to be the most stable. So even though we know 3 is a primary carbocation, because it's in a benzoic position, it's going to be really stabilized. Even more so than, let's say, even more so than this one right here. Because this is a tertiary carbocation resonance stabilized. But even this is less stable than a benzoic position. So we have our 1 right there. So now we need to figure out 2 and 3. So we see here we have resonance stabilized tertiary and resonance stabilized tertiary. Now, what's around it is we have a propyl group and CF3. Now, if we remember, CF3 is a strongly electron withdrawing group. So let's think about what that does to a carbocation. Since we have a positive charge, we could say that is electron deficient. So what do you think is going to happen if I pull away electrons from something that's already electron deficient? It's going to make it, exactly, Matthew, it's going to make it more unstable. So for this reason, I would say this is 2 and this is 3. All right, so now for our last two options, I don't even have to compare to know which one's unstable. It's going to be this radical or carbocation right there. And that's because we never want carbocations, carboanions, radicals on vicinal positions or directly on the double bond. That makes it extremely unstable, so we know that's always going to be like our last option. Okay, so question 2 talks about, let me see, looks like we're going to do reaction mechanism. So we have initiation, propagation, and termination step. So I'm going sort of based off memory, so let's see. Let me see here. Let's start with the bromine Br2. What happens is we have some light coming in and breaking the bond. And so what we do is we form two radicals like this. So now we get bromine radical, like so. This is known as the initiation step. So initiation is the formation of the radicals from light. Next, we'll have one of the radicals, let's pick this one. We'll have it react with a hydrogen on a stable position. So I'm going to pick the tertiary position because it's the most stable for a radical. And what's going to happen is this is going to, one of the electrons is going to form a bond with this radical, and the other one is going to go onto the carbon. So we get this structure. This is known as the propagation step. And so finally, what's going to happen is this is going to repeat for a couple of times, creating a bunch of molecules like this. And the last step is going to be the elimination of the radical, where we have this bromine, so we have this carbo radical react with a bromine radical to form our bromination product. Now, some important things I want to highlight is that every time I'm drawing bonds or connecting bonds, I'm using like a half arrow like this. So when you see an arrow like this is to indicate two electrons moving, or one pair. When you see an arrow like this would indicate one electron moving. Okay, so this is the notation we're using for radical formation, because as we know, a radical is just one electron. And so one electron is forming a bond here, and then one electron is coming to form a bond there. So whenever you're drawing mechanisms for radical halogenation, you should always be using the single arrow like this. Okay. Does anyone have any questions about this before I move on to the next slide? All right. You had a question? Oh, you're talking about the first question. Okay. Why is it 2, 3, 1? Okay, sure. So what I did first was I picked out all of the resonance structures from this list. So we had 3 resonance structures, and now I want to figure out which one's the most stable. So I picked one as the benzylic position because the benzene creates the most resonance structures, and so this is going to be the most stable. So that's why this is going to be 1. Now, between these two, I have a tertiary carbocation that's resonance and a tertiary carbocation that's resonance. So, since both of those things are the same, we have to look at inductive effects or neighboring groups that can help stabilize the carbocation. So here we just have some electron donating groups, and here we have an electron withdrawing group. So CF3, because fluorines are highly electronegative, they're going to steal away some of the electron density from around this area. So if you think about it, a carbocation is electron deficient, right? Because that's how you get a positive charge. You're missing some electrons. So if I'm pulling away more electrons from this positive charge, that's going to make it even more unstable, right? So because the CF3 is pulling electrons away from a carbocation, it's going to create instability. And so this is why this is going to be 3, so it's less stable than 2 over here. Does that sort of answer your question? Okay, so now let's move on to the next page. Okay. Rank by rate of bromination on the hydrogen indicated. Okay, so here we have some different hydrogens here that we're going to take a look at. And so what I want to do first is label out sort of each hydrogen. So from right here, I see that this is going to be tertiary. This is going to be secondary resonance. This is going to be primary. This is going to be tertiary. And this is going to be secondary. Okay, so let's try another poll. All right, so out of all of these 5 options, which one is going to be the most stable? All right, good. Yes, number 2 is going to be the most stable because it is the only resonance stabilized bromination out of the 3. So now we're going to take a look at, I'm going to compare these two tertiary brominations right here. Because as we know, bromination involves a radical, and radicals like tertiary positions. So based off of these, there's going to be one that's particularly more stable than the other. So I want you to click yes if this molecule is going to be more stable, or no if this molecule is going to be more stable. All right, we have 1 vote for no. And you are going to be correct. So this is going to be 2, and this is going to be 3. And so the explanation is it matches with what we were talking about with carbocations. We have, when we form the radical, what we'll see is a structure like this. And let's say there's a leaving group like CF3. So a radical is similar to a carbocation in that they're both electron deficient. So when you have a strong electron withdrawing group like CF3 pulling electron density away, it's going to once again destabilize the radical. right? So think about carbocations and radicals as they're very similar to each other. They're both electron deficient, so they both prefer tertiary positions, and they both dislike electron withdrawing groups. So now that we have that, oh sorry, this was actually supposed to be 2. Let me erase that. And so the last few ones are pretty easy to figure out. So we're just going to do normal carbocation stability. So this is going to be 4, and this is going to be 5. Okay. Find the number of monochlorinated products for each of the following molecules. So with monochlorination, there are 2 things to consider. One is that you want to find places where there are hydrogens that are relatively stable. And 2, you want to make sure that you're not having any symmetry. Because a lot of the time, if I have something like this, these 2 are going to be the same product. Now, this chlorine might be on opposite sides, but because molecules are in 3-dimensional structures, I can flip one of the molecules over and get the other one. So there's the same product. So in this case, we're going to say there's only one monochlorinated product amongst these 2, right? You wouldn't consider these as 2 separate. So let's take a look at the first example, where we see that we have one possibility right here. So that could be one monochlorinated product. There can't be any monochlorinated product on this central carbon right here because there's no hydrogens. You need a hydrogen for monochlorination and monobromination. And so I'm going to say this has one monochlorinated product because, as you notice, these other groups around it are identical, right? They're all CH3 away from a quaternary carbon. Right? So because there's a symmetry, we're only going to consider having one monochlorinated product. In this example, because there is no symmetry, we're going to have 1, 2, 3, 4. In this example, what I like to do is I like to draw planes of symmetry. So we can draw a plane of symmetry going down like this and going across like this. So now we see that there are 2 monochlorinated products, one here, one here. Because as we'll notice, this product corresponds to this one. This product will correspond down here and across. So that's why there's only 2. If we take a look at this one, we can see one product in the center, one here and one here. And so there's going to be a total of 3 because the other groups are identical, right? This is an ethyl going this way and the ethyl going this way. So these 2 groups are identical along with this ethyl going down. So because they're all ethyls extending out from a CH, they're going to be identical, so we only have 3 products. Sort of. It's kind of weird to draw in the 3 planes of symmetry. Let me try it. So if we draw it out, it might look like this. right? So yeah, if we draw it out like this, there is a third plane of symmetry, but it sort of overlaps with what we're looking at. But when you draw it out like this, you can see that in this quadrant right here, there's 3. So this corresponds to, they'll overlap this way and they'll overlap this way. So that's why there's only going to be 3 monochlorinated products. For the other one, oh, you mean like a diagonal plane of symmetry? I guess I can see that actually. So you would mean like this, right? Oh, I see now. Okay, yeah, you're good catch. Right, so there is that third plane of symmetry here that connects these two. So because of that, there's actually only going to be, where's my eraser? There's only going to be one monochlorinated product here because of that plane of symmetry. Yes, I think I was thinking about a different example. But yeah, because there's that plane of symmetry, this one no longer is a separate product. So there's only going to be one. Now, if we move on to this one, we have one plane of symmetry right down the middle. So we're going to have one example here and one example right there. And there's going to be another one here. Now, is there going to be another one on this carbon right here? No, because once again, there's sort of some internal symmetry, right? Where these are 2 methyl groups sticking out from this carbon right here. So that means these 2 are identical to each other. So that there's only one monochlorinated product amongst the 2. So we can say that this has 3 monochlorinated products. Okay, anyone have any questions before we move on to the next problem? Okay, so now the next question is talking about discuss how we decide on basicity and nucleophilicity rankings. Consider ways that these terms are similar and how they may differ. So if we remember our acronym, we have B, E, A, N. So these are similar in that we're both looking at negative charges that are reactive. So in both scenarios, we have a leftward trend this way. Because negative charges actually become more stable as they're on this side over here, because these are where the electronegative atoms are. So if there are electronegative atoms, they stabilize the negative charge, but we want an unstable negative charge or a reactive stable negative charge. So those are the ways bases and nucleophiles are similar, but the key difference is that nucleophiles like to increase in size. And so the reason for this is that they're less likely to be solvated around by charges. So because of that, nucleophiles prefer to be cut larger, but bases prefer to be smaller. And so this is the difference in trends between bases and nucleophiles. So some strong nucleophiles and bases we should consider are, so a category are, we can have 2 categories. We can have nucleophile bases, nucleophiles, and only bases. So these could be N minus, O minus, SH, right? A lot of these can be strong nucleophiles and bases. Sorry, not SH. SH is too big. For nucleophiles, we can have larger species. Let me think. Let me look at the chart. So for some strong nucleophiles, we can have Cn minus, N2 minus, N3 minus, excuse me, and SH. For bases, we have the typical bulky bases that are going to be good bases but very bad nucleophiles. And so our two well-known ones are LDA and tert butoxide, which looks like this. Okay, so these are some strong nucleophiles and bases we can look out for when we're considering substitution elimination reactions. And so these are key factors in sort of differentiating, oh, is this going to be an SN2 or is this going to be E2? Because remember, SN2 can only use strong bases, strong nucleophiles, while E2 can only use strong bases. So even if something is really stable for SN2, if there isn't a strong nucleophile, we can't do SN2. All right, so are there any questions before we move on to the next page? All right, so let's move on to 3. So now we have rank by SN1 reactivity. The substrate with the fastest rate is 1, while the substrate with the slowest rate is 5. So when I look at this problem, I see a bunch of groups with a bunch of halogens. So we're looking at the substrates that the nucleophile is going to attack onto. So with SN1 reactivity, what they're really asking you to do is rate by carbocation stability, right? Because SN1 involves the formation of a carbocation. So we need a carbocation to be stable first. So let's rank by positions. We have secondary here, secondary here, secondary resonance, tertiary, and primary. So we know that the best stabilized SN1 substrate is going to be this one right here because of the fact that it is secondary, but it has a resonance structure. We also know what the worst one is going to be. This primary one over here. So that's going to be 5. Now, if we keep moving down the line, the one that's going to be the next stable is going to be this tertiary one right here. So once again, we have two options. They're both secondary, but how do we figure out which one's going to be more stable? Okay, thank you for joining us, Matthew. So between 1 and 2, which one do you think is the better SN1 reactive group? Let's check our periodic table for a second. So actually, 2 is going to be the better group because we've ranked by carbocation stability, and the carbocations have the same stability. So now we have to look at the other part of a substitution reaction, which is the leaving group. So if you remember, iodine is a better leaving group because it's more stable when it leaves, because it's lower on the periodic table, right? So because iodine is a better leaving group, this is going to be 3. Oh, okay, I see. Yes, then yes, you are correct. The group with iodine is going to be more stable than the group with bromine because they're both secondaries. So now we have to consider the leaving group. So this is going to be our ranking. So now if we do this one, this is now SN2 reactivity. So SN2 reactivity goes primary, secondary, tertiary. And methyl. Methyl just means it's just a leaving group connected to one carbon, like in this example right there. So that's going to be the most stable. If we look at the other groups, we have a primary here, a secondary here, secondary, and secondary. So when we have issues like this, what we're going to do is we're going to rank by its neighbors. So right, because this is a secondary next to a tertiary. So it's not going to be as stable as a secondary next to another secondary or primary like this. And so if we do our ranking, we can say this is 2 because it's a primary. Let's say this is 3, 4, and 5. Right? No issues there, right? But a problem is exactly as we notice, when we look at its neighbors, we see that this group right here is a quaternary carbon. So because of the fact that it's quaternary, we know that this is always going to be the least stable. And so we'll say this is automatically going to be 5, and this is going to be 4. So based off of these two groups right here, we know this one is going to be less stable because it is a secondary next to a tertiary, while this group has a secondary next to a primary and next to a secondary. So it's not as sterically hindered as being next to a tertiary group. Okay, so now we're going to move on to some reactions. So we're going to find the major product for each of the following reactions. So all of these involve weak nucleophiles or weak bases. So we're going to do either SN1 or E1. So in both instances, we're going to form the carbocation. That's going to be similar for all of them, right? Because SN1 and E1 both involve the formation of a carbocation. So once we form the carbocation, we have to make sure to be able to do rearrangements to make it more stable. So here I can do a methyl shift to move that down to create this. Oops, sorry, that's wrong position. So now I can it's simply a matter of figuring out what to do. So for SN1, we're just going to substitute a nucleophile or water like so. And so it's going to look like this. For E1, we form a double bond, and because this is elimination 1, we're going to say we're going to form the Zaitsev product, which is going to be right there. So those are our two options after we've formed the most stable carbocation. Moving on to the next one, we have H2SO4. So what this does is that this causes OH to become a more stable leaving group. So we see that it becomes OH2 positive, which can leave, so you get positive charge like this. And so this is already in a pretty stable spot. I don't think we can shift it anymore to become more stable. So we're going to leave it like that. And in this case, whenever you have something like H2SO4, this is going to be a double bond favored reaction. Because what happens is you have HSO4 minus left behind, which is a base. And so you form the double bond like this. So whenever you see H2SO4 and OH, you're going to be forming a double bond. So now, yeah, sure. Let me just give me a second, just looking at the key to see if I'm missing anything. Okay, I see. All right, so back to explaining this. I'm just going to erase everything for a second. So H2SO4 is an acid, and OH is sort of considered as a base. So what we can think about is that this OH is going to grab this acidic proton from the H2SO4 like this. And so when it does that, it's going to form OH2 plus. And so this is a good leaving group because when it leaves, you form water, which is stable. And so now you have left behind a carbocation. Because HSO4 minus is a base, this is now going to cause the elimination product to be formed like this. Now, let's say, for example, we had something like, let's say we had HBr. So HBr is also an acid. And so it's going to give up a proton to OH to form OH2. This is going to become a leaving group, and we're going to form the carbocation. But in this case, our leftover is Br minus. So Br minus is considered a better nucleophile than it is a base. So now this can attack here, and we can form instead the substitution reaction, which looks like this. Br. So does that sort of make sense for everyone? Right, in this example, there is no SO1 because we have H2SO4. If I did HBr, then there would be SN1 because Br is a better nucleophile than it is a base. It's sort of about what's left behind. We're leaving behind a base, bases do elimination. But if we're leaving behind a nucleophile, that's going to do substitution. Okay? So now for our last one, I think there should be a bromine right there. But what we're going to do is, let me erase some of this. So we have a nucleophile and we have a bromine with some stereochemistry on it. So if we actually look at our table that's in the slides, we see that our NH2s are actually strong nucleophiles. So this is actually going to be forming an SN2 reaction. And so it's going to do a backside attack, and bromine's going to leave, and we're going to be forming this structure here. And so we see that inversion of stereochemistry because this is actually an SN2 reaction. I think the question sort of got cut off because I think this reaction, this part up here is supposed to be SN1, SNE1, but the rest of them aren't supposed to be SN1, E1. So this is actually just a normal SN2 reaction. Right, because we have a strong nucleophile, we have a good leaving group, and so we're going to have an inversion of stereochemistry in this structure right here. So if it's uncharged, you deprotonate, right? Okay, so I guess now might be a good time to sort of explain why we deprotonate it. So initially, we would form this structure right here. And so if we think about the formal charge of nitrogen, nitrogen right now has 4 bonds. So if it's 5 minus 4, this is 1. So it's going to have a plus charge right here. So that makes one of these hydrogens more acidic. So something like water can grab a hydrogen and bring a lone pair to nitrogen. So now it looks like this. And so this is called acid workup. So yes, if it's uncharged, you deprotonate it because what happens is when you form the bond, you form a new charge on it. And so to deprotonate it, you're getting rid of that new charge you formed to make it more stable. So that's known as acid workup, and we assume that for every sort of reaction. You would always just draw the reaction after you've done acid workup. Okay, so now I'm going to move on to the next page, which will probably have some more reactions if no one else has any questions. All right, so I'm going to move on now. All right, so now we just have some classic reactions here. So we see first we have NaBr with tertiary iodine. And so if we look at Br minus, this is not going to do an SN2 reaction because it's tertiary, but I would say this is going to do an SN1 reaction. And so this is the case because Br minus is a better nucleophile than it is a base. And so because of that, we're going to do a simple substitution where we form the carbocation first. We have Br minus attack like so, and we're going to form this product right here. For our next example, we have Cn minus, and we have a primary leaving group. So we have a primary leaving group, and we have Cn minus. This is probably a very good SN2 reaction. And so this would attack at this position, this would leave, and so we would get Cn right there. So we have 3 options right here. We have LDA, KOH, and I minus. So LDA is known as the bulky base. So we're going to do the E2 product for this. So we have two options of hydrogens. We can either pick this hydrogen here, or we can pick this hydrogen here. Because it's a bulky base, I'm going to pick to create a double bond there. Because as we remember, bulky bases create the Hofmann product, which is the less substituted product. Now, if we do KOH, we have OH minus. This is a strong nucleophile and a strong base. So my question is, do we think it's going to prefer an SN2 reaction or an E2 reaction? Okay, we have one answer for SN2. Does anyone else think differently? Okay, so we have E2 and SN2. So let's talk about it. So whenever we're going to be comparing something like this, yes, we have to look at steric hindrance and its neighbors. So the first thing I would consider is where the leaving group is on. So this is secondary leaving group. So it's not too unstable for SN2, and it's not too much preferred for E2. So it could go either way. So next we're going to look at its neighbors. And so it has a tertiary neighbor. So because of the fact that this is a tertiary group right here, this is going to cause steric hindrance for SN2. So E2 is going to competitively win. And so what that happens, you form the Zeitz product like this. So this is why E2 is going to be the major product. Now, if we look at I minus is a strong nucleophile but a weak base. So because we have a strong nucleophile and weak base, now we're going to be forming the SN2 product, right? Because we can't even form the E2 product. To form E2, you need a strong base, and this is only a weak base. And so now you would do something like this. Okay, so those are the three different products we can get. We got a Hofmann product, we got a Zeitz product, and we got a substitution product. Yes, exactly. There's no stereochemistry because they don't show wedges and dashes. If this bromine was on a wedge, then of course we would flip it into a dash. But because they don't show it, we don't need to put it on. Okay, so now let's move on to the next question. Okay, so we have SH minus. So this is, if we memorized our table, this is a strong nucleophile, weak base. So we're probably going to be doing SN2, but let's check. So what I like to do is, if I ever have a Fisher projection like this, I just like to draw it out in line angle. So we'll draw the bond right here. There is a CH3 sticking out like this, and we have deuterium like this, and we have Br in the back. So it doesn't look like it's too stable, or sorry, it doesn't look like it's too sterically hindered. So we're just going to do, a backside attack like so, and we're going to form this structure right here. Now, so this is the way I like to do it. We can also sort of do it in the other way, which is if we wanted to show the inversion in the Fisher projection. Because I know this is an SN2 reaction, I want to show stereochemical inversion. So we're going to do this. D, and I'm going to put SH here and H here. So by putting it on opposite sides, I've shown that there's a stereochemical inversion around this chiral center. So by swapping that, this is how you can show inversion on a Fisher projection. But for me personally, I like to just go to a line angle so I can see the whole, I can compare neighbors easily, and then I just do it from there. For our last example, we have a strong nucleophile and base. And we have a secondary leaving group. However, we'll notice that we have a quaternary carbon right next to it. So because of this, we can't do SN2. So we have to do E2. But because of stereochemistry, we now have to consider anti-coplanar. So this is the rule with E2 that says that the bromine and the hydrogen have to be anti-coplanar to each other. So if we draw out the bond, we see we have, I'm going to say this is the R group, like here. And so we have bromine here, and we have hydrogen. And up here we have this group like this. We have hydrogen in front, and we have CH3 like this. And so what I'm going to do is I want to rotate this. We're going to rotate the single bond so that we have our desired bromine and hydrogen positions. So I want them to look like this. Hydrogen up, bromine down. And so if I rotate it this way, we get hydrogen in that position. We get the ethyl group in a wedge, and we get the CH3 still on a dash. However, now we're going to look at the other carbon to make sure we're rotating that as well. So if you bring this bromine here, we have this R group coming towards you, and we have hydrogen going to the back. And so this can sort of be explained by, if you're having trouble seeing it, R is like this, bromine is here, hydrogen is there. So I'm going to bring it down here so that it looks like this. So now R is on this side and hydrogen is on this side. It's sort of like I'm spinning a steering wheel, right? Everything changes when I rub bromine with it. And so the R is coming towards you, the hydrogen is going away. So because of the fact that bromine and hydrogen are now anticoplanar, we're going to just draw out our double bond. So what I do first is I'm going to draw the double bond like this. And on one side, I'm going to put everything that is a dash. So let's pick here a hydrogen and CH3. On the other side, I'm going to pick everything that's a wedge. So the R group and the ethyl group. So this is our final product. All right. Anyone have any questions? I know this one was a little bit more tricky because of the rotation, but hopefully I didn't go too fast. All right, let's keep continuing. I think we're making good time here. All right, so now we have some more reactions. We have NaOET. So this is strong nucleophile, strong base. So our next step is looking at the leaving group. So because this is a tertiary, I'm going to think this is going to do an E2 reaction. So because of stereochemistry, we once again have to consider, are the bromine and the hydrogen anticoplanar? So over here, there's a hydrogen on a dash. So because bromine is on a wedge and hydrogen is on a dash, we can now form this product with no problems. And this is because bromine and hydrogen have opposite stereochemistry. So this, you can use this technique when we're talking about on a cyclohexane. I wouldn't recommend using like opposite stereochemistry like this if you're talking about a single bond. I would recommend doing it the way I showed you, which was rotating it to make it into the plane. So that is just O minus with, like so. The ET stands for ethyl. So it's basically saying you have oxygen with a negative charge attached to an ethyl. So now we're going to do a bromination. So what we do first is we're going to remove the most stable, we're going to form the most stable radical, which is going to be right here with this hydrogen gone, right? This is our propagation step, but because this is resonance stabilized, I'm going to resonate with this radical to see if there's a more stable position. So when I do that, I get this. So now I've gone from a secondary radical to a tertiary radical. So now this is going to be the more stable position, and we're going to form this product. So whenever you have something like this is sort of like with rearrangements, right? You need to look at both the resonance structures in order to figure out if there's a more stable position. If there is, then the bromine is going to react more specifically with that resonance structure, right? Because they're both resonance stabilized, but one of them is a secondary radical, while the other one is a tertiary radical. So that's why it's more stable. In this instance, we have a bulky base. And so whenever we have a bulky base, we're going to do E2 Hoffman. And so this right here is more substituted, but this right here is less. And so our product is going to look like this, where we form the Hoffman product because it's the bulky base. So now we have a pretty interesting reaction here. This is called vicinal dibromide reaction. And so what happens is that the two bromines sort of act like leaving groups and hydrogens, where you have I minus attack a bromine, bond forms here, and this leaves. So whenever you have bromines next to each other on opposite stereochemistry, using Ki, you're going to form a double bond in between like this. This is going to be a question on your test. And it can be a very easy point. So be sure not to miss this question right here. Just know that if you have bromines next to each other that are opposite stereochemistry, using Ki or NaI or just like a halogen like this, you'll form a double bond in between. So for the last one, all it says is that we're adding heat. So it looks like there might not be any reaction. But what we see is that we have a leaving group here, and we have an NH2 group right here. So this is known as an intramolecular substitution. And so this NH2 is going to attack right here. This is going to leave, so we form 1, 2, 3. A three-membered ring. So this is the intramolecular attack. Oh, can this intramolecular, which one are you referring to? Are we talking about the vicinal dibromide or the intramolecular substitution? Okay, for the vicinal dibromide, yes, you can have that happen even if it's not on a ring. You just need the two bromines to be opposite stereochemistry or anti-coplanar, right? It's like E2, right? You need the hydrogen and bromine to be anti-coplanar. So in this example, you just need the two bromines to be anti-coplanar. That's the whole reason why it does this reaction. Okay, any other questions before I move on to the next page? The heat is trying to show that it's just there to be like this is gonna initiate the reaction. But what it's trying to tell you is that we're not adding anything, so that means there's probably going to be an intramolecular substitution, right? And so that occurs because we have bromine, the leaving group, and we have the nucleophile on the same molecule. So they can form a ring with each other. So heat is just trying to say, we're not going to add anything, but we're going to start a reaction by just adding heat. What if heat is combined with another solvent? That's a good question. I think it would still do this reaction. Because a solvent, like, if we said the solvent was like CH3OH, that's still a weak nucleophile. So it's not going to beat out the strong nucleophile, which is NH2. So the solvent won't do anything either. Oh, Katie, did you get to hear my explanation? Okay, good. Yeah, so basically I was saying it's just, even if you have a solvent, it's not going to be stronger than like a strong nucleophile, right? So it's not going to like beat out the nucleophile in this case. If they said heat and like a strong nucleophile, I'm not quite sure. I don't think they'll do that. That gets too confusing. Okay, so if no one else has questions on this page, I'm going to move on to the next one. Yes, I do think this intermolecular substitution was on your last quiz. I know I made this problem personally, but maybe I think I might have stole inspiration from when I took that quiz. NBR. NBR. I'm not sure what NBR is. Are we talking about an NBS? NBR and CH3. So it was still the intramolecular reaction, but with NBS? Because NBS is indicating a bromination now. That's like a different type, like, that's a different reaction altogether. Oh, okay. So that might, but similar ring. Okay. Did it have the nucleophile? Did it have the, oops. Did it have the nucleophile like this? And the bromine on the same ring? It had a bromine. But no nucleophile. I think in that example, yeah, I'm not quite sure about that one. I think if it looks something like this, if it looks like this, then we have NBS heat. I think this is just a normal bromination because NBS is a brominating product. And so it's a monobromination product that instead of using light to form a radical, you use NBS. And I guess heat can be a reactant to kickstart the reaction. So I think in that case, it's just a normal bromination. But here, heat is to kickstart the intramolecular substitution using NH2 and Br. Okay, that's good. All right, so now I'm going to move on to page 6. Okay, so now we have something that we might not be familiar with. We have AgNO3. So can anyone in the chat tell me what AgNO3 does? SN1, exactly. So to explain the mechanism for people who aren't familiar, when you put AgNO3 in water, it splits into the Ag plus ion and the NO3 minus ion. So Ag plus ion can react with bromine to form AgBr. If you remember your solubility rules, you know that AgBr is insoluble in water. And so it precipitates. And so what happens is that what's left behind is a carbocation on this position. And so the whole reason we're doing this is that because primary carbocations are unstable. So if we wanted to do an SN1 reaction, it wouldn't be stable. It would take a while to do. So in this way, we can form a carbocation relatively quickly and so we can do the SN1 reaction. So the first step is we remove the bromine and we form the carbocation, like so. And so we always need to check for rearrangements when we're doing carbocations. So what we do is we check 1 for a hydride shift and 2 for a methyl. So because there's no hydrogens here, I'm going to move this methyl group up there so that we can get this product right here. So we have a tertiary position with CH3OH. So I'm going to do an SN1 reaction. So I'm going to substitute the positive charge with our nucleophile, and we're going to get this answer right here. So to summarize, AgNO3 causes the formation of a primary carbocation. We can now rearrange the primary carbocation using methyl shifts. So we did that and we got a tertiary carbocation. And now CH3OH as a solvent will act as a nucleophile and substitute onto that tertiary position. Now for our next example, we have a bromine and we have KOTBU, or tert butoxide. So this is, again, a strong base, a bulky base to be specific. And so we're going to do the E2 product. So first we need to check if there are any hydrogens nearby that we can react. So we have one hydrogen, we have two hydrogens here, and we have a hydrogen right here. And so these two hydrogens are anticoplanar, so you could form a double bond between them. But because we're looking for the Hofmann product, the Hofmann product is the less substituted elimination product. So what it's going to form is this. if you remember, the other product is known as the Zaitsev product. So we don't form the Zaitsev product in this case because we have a bulky base. All right, so now we're going to do some synthesis problems, which I always felt like was like the best part about CHEM, doing synthesis. And so the technique I like to use for synthesis is I start from our final product and we go back one step to see what we need to do. And then once I have that product, we'll start from the beginning and try to create it there. So it looks like we have a chain with a double bond. So let's think about what we already know. We know brominations, we know hydroxyl groups, we know substitutions, and we know eliminations. So in order to form a double bond, this would mean we need to do an elimination, right? So for eliminations, we need a bromine first. So let's draw out some possible areas where we could have a bromine. So we could have two options. We could have a bromine on this carbon right here, or we could have a bromine on this carbon right here. Okay? Now that we figured out two possibilities for the product right before, we're going to look at this one right here and see, okay, can we get to that there? So this looks like, okay, let's do a bromination and get there. But the problem is that brominations prefer the most stable carbon, this carbon right here. So we know that if we do a bromination, we're going to get this bromine right there. So the other bromine is out of the question. So we have two steps right now. But now the hard part is, how do we get from this bromine to this double bond right there? Anyone in the chat have any ideas? What can we use to get to that double bond? Exactly. Yes, we can use a bulky base, because if we used a normal base, then it would just form the Zaitsev product. But by using a bulky base, we can now form the Hofmann product, which is what we see. So I'm going to use LDA, and so that's how we complete our cycle. We start at step 1, which is Br2 with light. Step 2 is using LDA to turn the bromination product to do an E2 reaction to form the Hofmann product. Okay? Anyone have any questions on that? All right, now I'm going to erase this and so we can work on the second one. All right, so now we're going to apply the same technique that we did before. We're going to start with this one and work one step backwards. And so it looks like, once again, we're going to be forming another double bond, right? Because in this product, we have a double bond. In this one, we have two double bonds. So we're going to form another double bond. So we're going to, once again, use this. So it could be here. Or it could be right here. Let me just type something in chat. Okay, so now we have two different options for bromine. So let's start from here now. To get to here, we can do a bromination again. But the same example last time, we can only form the most stable bromine. And so in this example, it's going to be right there. That's going to be the most stable bromination. And so this product can't exist. And so we've got here. And now to form the other one, we can use a base like Na. Well, yeah, let's still use LDA. So I was going to use NaOH, but the problem is that it might also form the SN2 product. That's a good question. The reason the benzylic position doesn't work is that there's already a double bond right there. And remember what we said, we don't like putting anything on a double bond that already exists. So we're not, the next best position is that resonance allylic position right there. So that's why we formed the bromine there. And then I'm going to use LDA, because if I use something like NaOH, this is a good base, but there's also a pretty good chance that it would just form the SN2 product, right? Because there's not anything really sterically hindering that. And so this will now form the double bond right here. So bromination first, and then once again LDA. Right? But it's all about the process. It's about looking at our final product and going one step back. I think it's called like retrospective synthesis, something like that. It's basically where you look at, retrosynthetic analysis. It's where you look at the final product, move one step back to sort of give you a new frame of perspective, and then you start solving from the beginning. So that's the method I always use, and I think it's been working pretty well for me. So I recommend trying to use that method. All right, so now our last page is some more synthesis problems here. So right here we have, let's see, we have a group, and we have the same group here. So I noticed some similarities in that we have this group, this carbon, and this carbon look the same, except that it's just now one of them has a double bond. So just to help myself, I'm going to orient it the same way like this. So it looks like we have a double bond, and it looks like maybe this could be an SN2 reaction, right? Because you have a nucleophile and there's like the stereochemistry. So maybe if we go back one, we can see that it might look something like this, right? So that would work pretty well, where you have a bromine. Oh, sorry, could you not move that? Okay, so where was I? Oh, yes. So I was saying you have a bromine in this position, and that's when it makes sense. We do an SN2, so you do NaOCH3, and that would remove the bromine and get this. So now to get from here, we can do a bromination from this product, right? And so when you do a bromination, it once again forms on the most stable product, so that would be right there, because that is an allylic position. And so that makes sense. So now, how can we get from our initial product to here? Well, we can do two steps. So first, we can do a bromination because we want to form. We need a bromine first, right? Because we can't do anything we can't form double bonds without a bromine first. So we form a bromine there because that's the most stable position. And then we go to here, we need to use a base. But what type of base should we use? We would want to use a bulky base. Exactly. Because once again, we have the Hoffman product. So to show it a little bit more clearly, we have this, and we have this is our desired product. And so if we did something like NaOH, which is not bulky, it would form this product right here, which isn't what we want. We want the bulky product. So that is going to be why we use a bulky base. So to summarize, we have our initial product that we brominate. After that, we use a bulky base to form the Hoffman product. We do a second bromination in order to form a bromine in this position. And then we're going to do an SN2 reaction using NaOCH3 so that we get this inversion of stereochemistry. Okay, anyone have any questions on that problem right there? All right, so now I'm gonna, all right, now let's move on to the next one. So this is a roadmap where essentially you start off with one product and there's like a bunch of different ways you can go. And you're just trying to figure out and fill in the gaps. So you have a bromine, you have a bromine on a dash, you have a CH3 on a dash. And so right here, it's telling you to do the E2 reaction. So first you have to check this is on a wedge, bromine's on a dash, so you can form this product like so. So now it's telling you to use hydrogen and platinum. So this is a reducing agent. I'm not sure if you guys have talked about this yet, but essentially all it does is it takes away the double bond. So we get this structure right here. So to do a bromination, we're going to pick the most stable spot, which is right there. So we do that. So now we have CH3OH, which is a weak nucleophile and a weak base. So we can do either SN2 or, sorry, SN1 or E1. So first we form the carbocation, and it's a pretty stable carbocation. So you can do either SN1 or E1. Either answer is correct, but I'm going to do SN1 because I feel like we don't give SN1 enough love. So that would give us this. So now let me just draw it again a little bit lower. So this is what we have. Okay, so that is G, our final product. Now, if we go the other way, we have what we see a bulky base. So this is going to form the Hoffman product right there. And so bromination, we have to pick the most stable spot once again. And so here we see there's two options. Because we're going to pick a resonance spot, it could be here or here. And so once again, bromination prefers tertiary, so I'm going to draw it like this. So we do CH3, CH2, OH, which once again is a bulky, sorry, it's a weak nucleophile, weak base. So we can do, again, the SN1 or the E1 product. So because last time I did the SN1, this time I'm going to do the E1. And so that's going to look like this. because we formed the carbocation here, and we can't form a double bond going this way, so we have to form it down like this. And so that's going to be our double bond like that. And once again, you can either do SN or E1. I just picked E1, for the fun of it, right? But there's nothing that indicates either or. So your professor should accept both of them. But other than that, that's going to be this breakout room section. So does anyone have any questions, or does anyone want to go back and look at the slides? Because I actually think this is a new update for e-learning. Before they didn't used to save it, but yeah. So you can go back through any of them, take a picture of the work. Yes. Yeah, now you can go back. You're okay to do that. So if you want any pictures of the work I did, just go for it. In the meantime, before you leave, we have a survey that we would like you all to fill out. It's just about the session. So it helps us, to know, like, oh, is there anything we can do better? Can we improve?